Okay, so for lab 2, we were asked to predict the motion of a falling object due to gravity, and I chose that object to be a ball, so the system is just a ball falling from rest due to gravity. And here's the video I used. Newton's second law states that the final velocity is equal to the initial velocity plus F net over m times delta t. And Newton's law can also be used to predict the final position, which is by the equation final position is equal to initial position plus v average times delta t. Another law to keep in mind is Newton's third law, which states that for every action there is an equal and opposite reaction, which sort of comes into play later on. So I put the system into Tracker and tracked the position, and this is what came out from the position versus time graph. The velocity was obviously increasing from each point to the other due to the force of gravity making the object accelerate. So the difference between every point and the other is increasing with every time interval. And if we flip the y-axis in Tracker for the coordinate plane, we would get a whole other graph, and it would just change all of our results. So that's interesting to look at. Then we move on to the computational modeling of the system, Python. So we start off by plugging in the givens. We use a juggling ball, so the mass of a standard juggling ball is just 0.3 kilograms, and we assume it starts at the position 0 and at rest, so the initial velocity is also 0 and the time is 0. After that, we plug in the constants. The delta t, we get that by using the frames per second for my camera, the iPhone camera, 33 frames per second. So I used 9 frames from 50 to 59, and the time difference between every frame is 0.033 seconds. The gravitational constant is just 9.8. J hat we use as 1, and the B I used was 0.0017. Then we go into the actual equations. I used the while loop, and the time was 0.297 due to the 9 frames I used, so it was 9 times delta t, which was 0.033, which gives us 0.3 pretty much, approximately. And the weight is just negative m times g times j hat for the unit vector. And the drag force, of course, is negative v times mag ball velocity squared times the unit vector. And the total force acting on our system is the weight and drag force. Then we plug in Newton's second law, the equations, with velocity final equals velocity initial plus F net over m times delta t, and xf equals xi plus v average times delta t, where x is position. Then we plug in this code to put arrows into our diagram that comes out when we run the module. I use arrow scale equals 70, so the arrows would be nice and clear. Arrow 1 position is ball position, and the arrow 2 is also ball position. And then just W times arrow scale and the drag force times arrow scale for the 2 arrows. And when we run the module, this is what we get. There's a diagram of the ball falling with the yellow arrow to show the force of gravity and the blue arrow to show the drag force acting on our system. And here's the graph of position versus time for our computational model of the system. And when we graph the information from Python, this is the graph we get. And then I compared it to the graph from the system, but this was Python without plugging in the drag force, so the position was an overestimate. And then I plugged in the drag force, and the drag force was too much, so it was actually an underestimate. And then I adjusted B, and it turned out to be pretty close to the actual system with minor discrepancies. So in this case, the model cannot be used to predict the terminal velocity because it was on a very short interval, 0.3 seconds, where the gravity is much more than the drag, so they do not really cancel out to get a terminal velocity. And if the object was thrown with an initial velocity, then yeah, it probably would have been the same in case of this system because it has a really low time. And we actually could predict the motion of the object using Newton's second law, so the experiment was a success. Thank you.